Hello, my name is Arihant Kumar, and my topic is pumped hydro storage modern innovations, in which I would be focusing on advancing grid scale energy storage through engineering excellence and technological innovation. In the course Advances in Energy Technology under Professor Sanjay Kumar. There are certain fundamental operating principles. The first one is energy storing phase, in which when there are periods in which the electricity generation is huge, it's excess, then the pumps utilize surplus power, the extra power, to transport water from a lower reservoir to an upper reservoir. This consumes electrical energy into gravitational potential energy. Then there is energy release phase, in which when the demand of electricity peaks, water flows from upper reservoir through the lower reservoir through turbine generators, and it again converts gravitational potential energy back into electrical energy for grid dispatch. Third is reversible turbine operation. Modern pumped hydro facilities employ reversible pump turbine units that can switch between pumping and generating modes. So there are two modes, one is pumping mode and one is generating mode. And the modernity lies in the fact that they are reversible. They can interswitch from one mode to another mode. This provides rapid grid response, regulation services, and frequency based capabilities. There are certain system efficiency and performance metrics. Round trip efficiency. Modern pumped hydro systems are said to achieve 75 to 85% round trip efficiency, with advanced designs reaching up to 87%. Energy losses occur primarily through friction in penstock systems, turbine inefficiencies, and evaporation from reservoirs. So there is this diagram, a schematic diagram of a pumped hydro storage plant showing upper and lower reservoirs, penstock, reversible pump turbine, and flow directions. So there is this upper reservoir which has water stored in it, and through a dam it is flown through a control valve. The control valve opens periodically and then it's shifted to a turbine. The turbine rotates, and through the rotation of the turbine, the motor or the generator unit generates electricity. The same electricity is transferred to transmission lines through a transformer, which upscales or low scales the voltage, and the remaining water is fetched to a lower reservoir. The same water is again reversibly taken up to the upper reservoir through the same valve, and this facilitates the duality. There are certain key performance parameters. The response time. The response time is 1 to 3 minutes from standby to full generation. Ramp rate, up to 100% capacity change per minute. Cycle life, 40 to 60 years of an average operational lifetime. Capacity factor. The capacity factor revolves around 15 to 25% for grid balancing and grid loading applications. And power density. Power density lies around from zero point 0.1 to zero point 0.2 megawatt per hectare, depending on the head height. Figure 2 shows a more modern or visually styled view emphasizing terrain elevation and water flow dynamics. There are different terrains subjecting to different geographical factors. So, based on those terrains, here is this modern and visually styled view in which we have the same upper reservoir dam, the generation and the pumping phase, the lower reservoir, and the central power station. There are certain recent technological advances from the year 2020 to 2025, in which there is variable speed technology, in which a doubly fed induction is implemented, and full converter systems enable continuous speed optimization across varying head conditions, which improves the efficiency and provides grid enhancement services, including power support. There are certain use of advanced materials as well, like high strength concrete with carbon fiber reinforcement, corrosion resistant coatings for marine environments, and certain composite materials for runner blades, which increase the durability while reducing maintenance requirements in challenging operational conditions. Digital twin integration. Real-time monitoring systems with IoT sensors, predictive maintenance, even edge AI, and algorithms and machine learning optimizations enable performance 24/7, which includes monitoring, reduced downtime, automated adjustments for maximum efficiency. Um, Underground pumped hydro innovations. What are the innovations which have come across in underground pumping? Breakthrough technology. Underground pumped hydro storage utilizes existing underground caverns, abandoned mines, or purpose built excavations as low reservoirs, dynamically reducing environmental impact and land use requirements while enabling deployment on flat terrain. There are certain engineering advantages: reduced surface footprint by 80 to 90%, enhanced security and weather protection, stable underground temperature conditions, utilization of existing infrastructure, and minimal visual and environmental impact. The figure 3 shows a schematic of hydro turbine cascade system with a bypass interconnections. It is a sequential or a cascade arrangement. Cascade means the flow arrangement of three hydraulic turbines: turbine 1, turbine 2, and turbine 3. These turbines have their own configurations and their own functionalities. In this configuration, the water discharged from an upstream unit is fed directly into the piping network that supplies the next downstream unit. Turbine the components labeled 1, 2, and 3 and the generating units. Connecting pipe. This is the main conduit that links the draft tube outflow section of one turbine to the inlet supply part of the next turbine. Seawater pumped hydro systems. There are three important aspects to it: coastal integration, corrosion management, and environmental considerations. Coastal integration talks about the fact that seawater pumped hydro systems utilize the ocean as the lower reservoir, constructing upper reservoirs on an elevated ground like coastal cliffs or artificial islands. This eliminates the need for two fresher reservoirs and enables deployment in water scarce regions. Corrosion management talks about advanced materials, including duplex stainless steel, nickel aluminum bronze, and specialized protective coatings ensure 30 plus year operational life in marine environments while maintaining high efficiency and reliability. Environmental considerations talk about closed loop designs that minimize seawater exchange, while fish friendly intake systems and environmental monitoring protocols ensure marine ecosystem protection throughout project lifecycle. This is a seawater pumped hydro system. The figure 4 talks about a seawater pumped hydro system. Global Project Showcase leading installations. So we talk about three leading installations in the world which are implementing this thing. The first is Bath Country Station, USA. The second is Tian Huangping Station, China. And the third is Raccoon Mountain, USA. Bath Community Station, USA has 3003 megawatt. Storage is 24 GH, world's largest pumped hydro facility. Um, the one in China talks about 1800 megawatt and 510 meters, located in mountainous terrain with exceptional head height. And the Raccoon Mountain, USA talks about 1652 megawatt, and the innovation is underground powerhouse, which features underground powerhouse construction carved into solid rock, demonstrating space efficient design and reduced environmental impact while maintaining full operational efficiency. There is this hybrid system integration in which we talk about solar arrays, which generate daytime power, feed grid and storage. Then we talk about wind turbines, which have intermittent generation, supply grid or charge storage. Then we have electrical grid and controls, which manages power flow, frequency, and dispatch signals. And at last, we have pumped hydro storage, which stores excess energy, provides backup and stabilization. Now we talk about certain performance statistics and market growth. 100 and what gigawatt global installed capacity as of 2024, representing over 95% of all utility scale energy storage installations. 40 gigawatt projects under development. New pumped hydro capacity in various stages of development globally, with significant growth in Asia Pacific and European markets. 87% peak round trip efficiency, maximum efficiency achieved by the next generation variable speed pumped hydroelectric systems with advanced turbine design. The operational lifespan of 60 years, expected service life of modern pumped hydro facilities with proper maintenance and periodic equipment upgrades. Now we talk about future outlook and engineering challenges. The challenges which we face are grid integration evolution, enhanced integration with smart grid technologies, real-time market participation, and advanced control system will optimize economic dispatch while providing essential grid services, including black start capability and renewable energy firming. Environmental innovation, development of closed loop systems, fish friendly designs, and habitat enhancement features will address environmental concerns while maintaining operational performance. Focus on biodiversity protection and ecosystem service integration. Cost reduction pathways. Standardization of equipment design, modular construction techniques, and advanced excavation methods will reduce capital costs. Target 20 to 30% cost reduction by 2030 through technological advancement and economies of scale. Thank you.